Okay, let's unpack something truly mind-bending. Why is gravity just so ridiculously weak?
It's a fundamental question, isn't it?
Yeah, we're talking about this chasm of 42 orders of magnitude
Hmm.
compared to, say, the electrostatic force. 42.
Wow.
Think about that. It's like comparing the size of an atom to the size of our entire solar system, and then doing that comparison roughly 5 times over. It's wild.
It really is. That scale is almost impossible to grasp.
And this colossal difference, it's known as the many orders of magnitude problem, or moon P. It's a major, major puzzle in physics.
Absolutely. What's fascinating here is that, this isn't some minor discrepancy. It practically screams that we're missing something fundamental about how the universe actually operates.
Right.
To give you maybe another sense of the scale, imagine trying to feel a single grain of sand while standing on a planet made entirely of magnets. Even that doesn't quite capture the weakness of gravity relative to electromagnetism.
Exactly. So in this deep dive, we're going to explore a really intriguing framework that attempts to solve this very problem. It's called the electrogravity magnetics construct, or EGM for short. And its goal is, well, nothing less than unifying Einstein's theory of general relativity with the often strange world of quantum mechanics.
That's the holy grail, essentially, unification.
Pretty much.
Mhm.
And the fresh perspective it brings, it focuses on the quantum vacuum.
Ah, the quantum vacuum. So if we connect this to the bigger picture, physicists have been chasing this unification of GR and QM for, well, decades now.
Decades, yeah.
And the EGM construct offers a novel approach by taking a closer look at this quantum vacuum. Now, traditionally, this vacuum is thought of as like a bustling arena of virtual particles constantly popping into and out of existence.
Right, like a sea of activity, even in empty space.
Exactly. But this traditional view, while it's useful in many ways, leads to some sticky theoretical issues.
Such as?
Well, like the idea of infinite energy packed into an incredibly tiny space is a bit of a mathematical headache, causes divergences.
I can imagine. So how does the EGM differ?
The EGM construct proposes a different picture. It suggests that the range or the spectrum of these virtual particles isn't infinite, but actually has limits.
Finite limits?
Finite limits, yes. And crucially, these limits are tied to the mass energy that's actually present in that region of space.
Okay, that sounds like it avoids the infinite energy problem right there.
It potentially does.
So this raises an important question. How does the EGM construct actually arrive at these finite limits? Where do they come from?
Good question. It builds upon the concept of the zero-point field, or ZPF. You can think of the ZPF as the quantum vacuum, but in a perfectly empty, flat space-time, no stars, no planets, nothing around a curved space.
The baseline vacuum energy, kind of?
Sort of, yes.
Huh.
Then comes in the polarizable vacuum model, or PV. Now, what's a really interesting twist here is that PV offers a reinterpretation of general relativity itself.
A reinterpretation. How so?
Instead of saying that space-time is inherently curved by mass and energy, which is the standard GR view, the PV model suggests that what we perceive as this curvature is actually a gradient in the quantum vacuum's refractive index.
Refractive index. Like how light bends through glass or water.
Exactly like that. Think of it like how light bends when it goes from air to water. The properties of the medium change how it travels. Here, it's the vacuum itself changing its optical properties, so to speak.
Ah, I see.
And crucially, matter is what polarizes this vacuum, causing that gradient.
Okay, so instead of space itself warping and bending, it's the fundamental properties of the vacuum that are changing locally.
Mm-hmm.
And matter is the agent causing that change.
Yeah.
That's a neat way to visualize it.
It is a different perspective.
And the EGM construct takes this PV idea a step further, right? It tries to find this fundamental connection between matter, electromagnetic energy, and gravity, all operating through this quantum vacuum.
That's the core idea.
And it uses some pretty sophisticated tools to do it, I gather. Things like Buckingham pi theory or quantized Fourier distributions. Sounds a bit technical.
It can get technical, yes. But at its heart, Buckingham pi theory helps us cut through the complexity of units, like kilograms or meters, to find the fundamental dimensionless ratios that govern the interactions. It helps find the essential relationships.
Like stripping away the complexity to find the core mechanics.
Precisely. And a key concept within the EGM construct that emerges from this is the unit harmonic operator, or UHO.
Unit harmonic operator. Okay.
Think of it as representing the number one pure unity, but broken down into its fundamental harmonic frequencies. A bit like how a musical note can be broken down into its overtones.
Right, the fundamental and its harmonics.
Exactly. In this case, the UHO helps represent mass energy itself as what they call the EGM spectrum, or EGMS. It's essentially a collection of these quantized harmonic frequencies representing the mass energy.
So in this view, matter doesn't just exist. It has its own unique energy signature in this frequency domain, this EGMS. Now, how does the force we actually experience as gravity emerge from this picture?
Okay, here's where it gets really interesting. When the EGMS of matter, its frequency signature, interacts with the zero-point field spectrum, which is that background hum of the vacuum and flat spacetime, it creates what's called the PV spectrum, or PVS.
Okay, EGMS interacts with ZPFS to create PVS.
Yeah.
Got it.
Right. This PVS represents how the presence of matter actually alters the spectral properties of the vacuum in its vicinity. It changes the vacuum's energy fingerprint, if you will.
Okay.
And the EGM construct, by using Einstein's equivalence principle, the profound idea that the effects of gravity and acceleration are indistinguishable.
Right, the elevator thought experiment.
That's the one. And by equating the density of mass energy to the spectral energy density of the surrounding gravitational field.
Okay, wait, spectral energy density, what's that exactly?
Think of it as how much energy is packed into each tiny slice of the frequency spectrum of the quantum vacuum. It's like detailing the energy content frequency by frequency.
Ah, okay, it's energy fingerprint, like you said.
Exactly. By doing that, the EGM construct can actually derive finite upper and lower limits for this PV spectrum, the PVS.
Finite limits again.
Yes. Now, this involves some complex math, integrating over frequencies and transforming things into a discrete Fourier distribution. But the core takeaway is that they arrive at concrete boundaries for this spectrum influenced by mass.
Okay, let me see if I'm getting this. If I'm understanding this correctly, gravity isn't like a fundamental force in itself in this model. It's more like a consequence, a manifestation of how matter interacts with the quantum vacuum spectrum.
That's a good way to put it.
And this interaction fundamentally changes the boundaries, the limits of that spectrum.
Yeah.
That's a pretty radical shift in how we think about gravity.
It is. It moves away from geometry as the sole explanation. And it has further implications, too.
Like what?
Well, the EGM construct doesn't just look at the overall interaction. It also delves into the idea that gravitational acceleration itself might not be smooth and continuous.
You mean it comes in steps?
Exactly. It might be quantized, come in tiny, discrete steps.
Quantized gravitational acceleration. So you're saying that if we could somehow measure gravity with enough precision, we might actually see it increase in these minuscule, almost imperceptible jumps.
That's the prediction, yes. By using the spectral energy density of the zero-point field and those quantized Fourier distributions we talked about earlier, the EGM construct arrives at a discrete spectrum for gravitational acceleration.
How small are we talking?
Incredibly, incredibly small. The prediction is on the order of 1028 meters per second square at the Earth's surface.
10 to the minus 28.
Yeah. To put that in perspective, it's like trying to measure the growth of your fingernail over the entire age of the universe. It's just far, far beyond our current ability to detect.
Okay, so while it's a fascinating prediction, we can't exactly run an experiment in the lab to see these tiny steps in gravity just yet.
Not with current technology, no.
But it does set the stage for potential future avenues of investigation, maybe decades or centuries down the line. Now let's circle back to the central puzzle. The many orders of magnitude problem, that huge gap. How does this EGM construct even begin to bridge this enormous gap between the strength of electromagnetism and gravity?
Right, back to the mu-and-p, this is where the concept of a phase difference becomes absolutely crucial.
Phase difference.
Yes. The EGM construct also quantizes electrostatic acceleration, using similar ideas, dimensional similarity, and that polarizable vacuum framework we discussed earlier.
Okay, so it quantizes both gravitational and electrostatic acceleration.
Correct. Then, by examining the ratio of the cubic frequency distributions of these two quantized accelerations.
Ratio, okay.
The MUGM essentially reveals its underlying cause within this framework. And the key insight here, the really elegant part, is that this massive difference in strength, the 42 orders of magnitude, is proposed to arise due to a 90-degree phase difference between the electrostatic and gravitational spectra within the quantum vacuum.
A 90-degree phase difference. So, like, they're vibrating fundamentally out of sync with each other in the vacuum.
Precisely. That's a great way to put it. This phase difference, according to the EGM construct, is the very reason why electrostatic forces are so overwhelmingly dominant, while fundamental properties like electric charge and mass remain independent of one another.
Huh, that's neat.
Mathematically, they derive a relationship that directly links the ratio of these cubic frequencies, these spectral properties, in the quantized electrostatic and gravitational PV spectra to the actual measured ratio of the electrostatic force, Fe, to the gravitational force, Fg. And that factor of pi over 2, which relates to 90 degrees, pops right out of the math.
Wow. So the incredible weakness of gravity isn't due to some inherent feebleness in this view, but rather a kind of fundamental spectral misalignment, a different kind of vibration in the quantum vacuum compared to the powerful electromagnetic force.
That's the interpretation offered by the EGM construct.
Think of it, the universe's most elusive force might just be out of sync with its most prevalent one. That's a really elegant and, frankly, surprising way to potentially resolve such a huge discrepancy.
Indeed. It offers a different kind of explanation than just assuming different coupling constants. And what makes the EGM construct particularly compelling, or at least worth looking at seriously, is that it's not just an abstract mathematical exercise.
Oh.
It has demonstrated some remarkable successes in aligning with actual experimental results.
Empirical validation. Okay, now that's interesting. In what areas?
Well, in areas like particle physics and cosmology.
Okay, you give me some examples.
Sure. For instance, the EGM construct has been used to theoretically derive the root mean square charge radius of the proton.
The size of the proton's charge distribution.
Exactly. And the value it arrives at 830.59 atometers shows a very close agreement with the experimentally measured value from the SELEX collaboration, which is 830.7 atometers.
That is close.
It is. And interestingly, the proponents of the EGM construct actually favor the SELEX value over the currently accepted CODATA recommended value, and they provide detailed reasoning for that in their online educational materials.
Okay. Any others?
Yes. They've also achieved good agreement in deriving the mean square charge radius of the neutron compared to experimental data. Getting these fundamental hadronic properties right is definitely noteworthy.
That's fascinating to see these theoretical calculations aligning so closely with fundamental properties of matter we can actually measure. What about when we look bigger, at the vast scale of the cosmos, and its successes there?
Absolutely. And this is perhaps one of the most striking examples.
Yeah.
The EGM construct's prediction of the Hubble constant. Back in 2008, based on this framework, they predicted a value of around 67.08 kilometers per second per megaparsec.
Okay, 67.08.
Now, what's truly significant here is that this prediction came 5 years before the Planck satellite's high-precision 2013 measurement, which settled around 67.3 kilometers MPC.
5 years before Planck, what was the accepted value back in 2008?
At that time, the official value from the Particle Data Group, the PDG, was significantly higher, around 73 kilometers MPC. So the EGM construct's prediction was much closer to what Planck eventually found, well in advance.
Wow, predicting a key cosmological parameter with that kind of accuracy years ahead of major observations. That's a pretty strong piece of evidence, you have to admit.
It is certainly compelling. Furthermore, the EGM construct has shown that a significant portion, they claim, over 23% of the astrophysical parameters listed by the Particle Data Group are fundamentally constrained by just one number, the temperature of the cosmic microwave background radiation, T0.
So things like dark energy density are tied directly to the CMB temperature in this model.
Yes, parameters like the density of dark energy, Arthur Enterboy, the baryon-photon ratio, the density of CMB photons, no, they argue these aren't independent free parameters, but are latched back to T0 through the EGM framework.
That suggests a deeper connection between fundamental constants and cosmology.
Exactly. The EGM construct also claims to offer potential theoretical resolutions to some long-standing cosmological mysteries, such as the early universe galactic formation problem, why galaxies seem to have formed so quickly, something the James Webb Space Telescope has highlighted, and also the cosmological flatness problem. They argue the EGM framework provides explanations for these.
So it's not just about tackling the weakness of gravity. This framework seems to potentially weave together explanations and make accurate predictions across a huge range of physics, from the subatomic to the cosmic scale.
That's the claim, yes.
That really does set it apart from some other theoretical approaches in this field, doesn't it? Like string theory or loop quantum gravity?
Precisely. While many other ambitious theories aiming to unify gravity and quantum mechanics, like string theory and loop quantum gravity, are often incredibly elegant mathematically, they frequently face significant challenges when it comes to direct experimental verification or making falsifiable predictions.
The testability issue.
Exactly. The EGM constructs grounding in quantities that can be, at least in principle or indirectly, measured or constrained at both the quantum and cosmological scales, is a key characteristic that distinguishes it.
And speaking of evaluation and scrutiny, I understand that even artificial intelligence has taken a look at the EGM construct. Is that right?
Yes, that's correct. Apparently, independent evaluations by advanced AI platforms like DeepThink R1 and ChatGPT 4.0 have assessed the EGM construct.
What did they look at?
They assessed it based on various criteria, including its potential to revolutionize physics, its scientific importance, its testability, and its overall value.
And the results?
Interestingly, both platforms consistently gave the EGM construct high marks, particularly in terms of its revolutionary potential and scientific importance. They also noted its relatively higher degree of testability compared to many other current frameworks in quantum gravity.
Higher testability. That connects back to what you just said.
It does. It highlights that testability crisis that people sometimes talk about in fundamental physics. The AI's consistent positive assessment, especially on testability from independent platforms, adds another interesting dimension to how this framework is being perceived.
That's truly intriguing. So even unbiased AI sees significant potential and relative testability in this approach. Now, of course, no scientific theory is ever the final word, right?
Absolutely not. Science is always evolving.
So what are some of the current limitations or areas where the EGM construct needs further development? It can't be perfect.
That's a crucial point to address. The EGM construct is definitely still an evolving framework. It's not presented as a completed theory of everything.
Right.
One current area of simplification involves the treatment of nonlinear graviton self-coupling, essentially, how gravity interacts with itself in more complex ways, which is a known feature of general relativity.
That sounds complicated.
It is. And future work will need to incorporate higher-order corrections for things like this and achieve a more complete integration with established methods like effective field theory.
Okay, so refinement is needed.
Definitely. And also, as we discussed earlier, that prediction of incredibly tiny increments in gravitational acceleration. While it remains a significant experimental hurdle, detecting those steps is just beyond us right now.
So it's a work in progress, but one with some compelling early successes and clear pathways for future investigation and refinement.
That seems a fair assessment.
Okay, so to recap our deep dive then, we've explored this EGM construct, a really fascinating attempt to solve one of the biggest mysteries in physics. Why gravity is so unbelievably weak compared to electromagnetism, the many orders of magnitude problem.
Right. And the core idea proposed by the EGM construct is that this apparent weakness isn't some fundamental disparity in force strength, but rather a consequence of a 90-degree phase difference.
A phase difference in the spectral properties of gravity and electromagnetism operating within the fundamental quantum vacuum.
Exactly. And we've seen how this framework seeks to unify general relativity and quantum mechanics by viewing the quantum vacuum not as an infinite void, but as having a finite spectrum of energies, a spectrum that is influenced and shaped by the presence of matter.
Yeah, the real aha moments, for me at least, come when we see the surprising connections it makes or claims to make between the properties of the smallest particles, like the proton and neutron radii, and the large-scale structure and evolution of the cosmos, like the Hubble constant.
And its potential to resolve some of these long-standing theoretical puzzles like flatness or early galaxy formation through this unique spectral lens.
Now, if you're listening to this and feeling like your brain just did a bit of a quantum leap, you're definitely not alone.
Yes, it's dense material.
It is complex stuff, and we've really only scratched the surface in this deep dive. If you're keen to explore this further, we highly recommend checking out the research articles we've drawn from Integrating General Relativity with the Quantum Vacuum and Resolving the Many Orders of Magnitude Problem.
And you mentioned they have educational materials online.
That's right. You might also find the EGM YouTube tutorial series. which is mentioned in the sources, a helpful resource for a more, maybe, visual and in-depth look.
Good resources to have. And perhaps the most thought-provoking idea to leave you, the listener, with is this. Could the seemingly vast and irreconcilable differences we observe between the fundamental forces of nature, could they actually be just different expressions, different vibrations or frequencies, perhaps, of the same underlying quantum vacuum spectrum?
If that's the case, what other seemingly unrelated phenomena in the universe might eventually be unified by understanding this fundamental spectral nature of reality?
It certainly offers a new and exciting perspective to consider, doesn't it?
It really does. Something to mull over.